Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video we're going to be looking at nucleophilic addition of carbonyls. So generically a carbonyl looks like this, where you have the C double bond O being the carbonyl group. And depending on what the carbonyl is, R1 and R2 can be different or the same. So R stands for rest of the molecule, and this is usually an alkyl group. What we mean by an alkyl group is something that has carbon and hydrogens. The R2 group here, which is on the other side of this carbonyl, can either be an alkyl group, which makes this whole pattern here a ketone functional group, or the R2 group can just be a hydrogen, and this makes it an aldehyde. Now, one important thing about the carbonyl group in both of these functional groups, ketones and aldehydes, is that the carbon itself is delta positive because you have a more electron negative oxygen. And this is really key because that means that the carbon in the carbonyl can act as an electrophile. This being an electrophile, it will be attracted to a nucleophile. We're just showing here with the Nu, and obviously the nucleophile can either be neutral, where it has just a lone pair of electrons, such as ammonia, or it can be negatively charged, such as the two that we're going to look at today, cyanide and hydride. We'll look at them in more detail later, but the really important thing at this stage is this nucleophile. It's the lone pair of electrons here that will attack the electrophile. And so we will push our double-headed arrow, double-headed because we've got two electrons here, onto the carbon of the carbonyl. This then forms a new bond between the nucleophile and the carbon. But remember, with this new bond to this carbon, the original carbon already had 4 bonds around it. 1, 2, 3, 4. And carbon can only have a valency of 4 bonds. So as you simultaneously form this bond, which ends up here, then you need to break one of these bonds that were originally there. And the one that is broken is the one between the C and the O. Draw from one of these bonds and you put it onto the oxygen, leaving behind a single bond to oxygen. Now the electrons that were in this bond, which are 2 electrons, because remember every covalent bond is 2 electrons. Here with just this H2 molecule, where you use a single covalent line, and that represents 1 electron from this hydrogen, 1 electron from this hydrogen. Just like that, we have 2 electrons here going onto the oxygen. Now the oxygen was neutral here, but now it has extra electrons, 2 extra electrons. It is negatively charged. Obviously, we have carbon now with only 4 bonds around it. So that's a top tip to always check whatever you draw, carbon always has only 4 bonds around it. And that's exactly why we knew, having formed this new bond here, which this arrow is representing, which is this bond here, that we had to change something, and that was breaking this bond in order to keep to this rule. Now the only other time would be obviously if you have a carbon carbocation, so C+, that would have 3 bonds around it. Now with this is fairly high energy, so we need to remove the negative charge here. And that is done by actually grabbing a proton, a H+, and it does this using that lone pair of electrons. Those electrons move, that's our double-headed arrow. Again, double-headed because there's 2 electrons, just like we had 2 electrons here, hence double-headed. Single-headed is only for radicals with 1 electron. And once we've done that, if you think, with that showing us, we're forming a new bond between the oxygen and this hydrogen. That is our product. Now this mechanism is called a nucleophilic addition. See, because we're adding a nucleophile to the carbonyl. So we're adding it because it's not a substitution, because nothing is switching over. It's only this particular species, whether it be cyanide or hydride, that adds onto the carbon to form this new product at the end. So this is an intermediate, and it's just 3 steps in the actual mechanism. Both the addition of cyanide and hydride follow the same generic mechanism that we've just looked at. But we're going to look at each one individually and just talk about some key features. So the first one we're going to look at is of cyanide. Cyanide as a nucleophile is this particular nucleophile here. Now what students often do is they're used to putting a lone pair on the nitrogen. This is really odd. It's where the carbon is actually has the lone pair of electrons and is negatively charged, and it will be the carbon that is making a direct bond to this carbon here. Thus, the product of this intermediate should be a carbon attached here and a nitrogen next door to it. Now then that leads to the product being like so. Now this product here is called a hydroxynitrile. The nitrile is due to this group here, hydroxy due to the hydroxyl group or the alkyl group. Now when we look at the cyanide nuclei in a bit more detail, see there's a triple bond between the nitrogen and the carbon here. So nitrogen is absolutely happy with this because nitrogen is neutral with 3 bonds around it. The carbon, however, just like we spoke about earlier, always needs 4 bonds around it. Here it has 3 bonds plus a lone pair, and it's this lone pair that makes it negatively charged. Now importantly, the product here, the hydroxynitrile, is really useful because what you've done in this process is you've extended the carbon-carbon chain. So here, this carbon here has made a new connection to this carbon, and carbon-carbon bonds are really useful. The other nucleophilic addition mechanism that you need to be able to do is that of the addition of hydride. Again, this follows exactly the same format, except this time your nucleophile is a hydrogen with a negative charge and a lone pair. And so you're forming carbon-hydrogen bond here and a carbon-hydrogen bond here. Now it's really important this because it is a reduction. If R2 is a hydrogen, what has happened is you have taken a aldehyde and you have reduced it down to a primary alcohol. And we know this product is a primary alcohol because the carbon that is directly attached to the oxygen has only one other bond to a carbon. Because remember, this R1 group is an alkyl group. Overall equation for this will look like this. As the source of the hydride is this sodium borohydride. Sometimes for simplicity, this is actually replaced by 2 square brackets H for 2 hydrides. Much like with oxidation with potassium dichromate, you'd use square brackets O for the oxidation. It's worth remembering to identify if you've got 2 square brackets hydrogen that this is a reduction, but also that you know that reduction uses sodium borohydride as a source of the H-. The other situation is where R2, so this group here, is an alkyl group. So let's just use a generic methyl group, CH3. This is the case. The only difference here is your initial functional group is a ketone. If you track the changes here, you end up with your product being a secondary alcohol. And that's because this carbon here, the one attached to the OH, is connected to 2 carbons. Just like before, we've got our ketone here reacting with sodium borohydride. It can be represented as the 2 hydrides for the reduction. So what I will recommend at this stage is, because they're so closely linked, the nucleophilic addition of cyanide and hydride, is to pause the video, turn off the screen or look away, and try to just recall the generic mechanism for nucleophilic addition of both a cyanide and a hydride. Okay, having done that, let's just see if you can just recall and apply this to 2 different scenarios. For each of these reactions, I'd like you to draw the product, and then I would also like you to draw the mechanism for how these products are formed. Please remember to use just this hydride anion as a representation for the sodium borohydride in your mechanism. So pause the video here and have a go. Okay, so the products that you drew down should look like this. The First one would be this hydroxyl. So we've got a secondary alcohol here, and this is the hydride that was formed from the sodium borohydride. Product for the addition of cyanide look like so. This is the hydroxynitrile. Remember, your carbon-carbon bond should be really clearly showing a C to C bond here. This bond can't be halfway in the middle. For example, that is wrong. Also, the carbon to the nitrogen is also wrong. So it needs to be carbon to carbon. Without saying, I'm just using coloured pen here just to really help track the changes. In the exam, you won't be able to do this. In terms of the mechanism, what we're going to do is just draw in the correct nucleophile and the electronegativities on the carbonyl of this ketone. We just put our hydride here. Then we're going to show these two electrons making an attack onto the electrophilic carbon. Then we draw the electrons from one of these covalent bonds. We're going to go from the middle, going onto the oxygen. This then leaves a negative charge on the oxygen, and that needs to pick up a hydrogen to complete and get to the alcohol. Get that from a proton. We just take the negative charge on the oxygen and the lone pairs that it involves to attack to pick up that proton, forming our secondary alcohol. Now, the mechanism for the hydrogen cyanide involves the addition of the cyanide nucleophile. Follows the same. We need to put the electronegativity on the carbonyl. Draw our nucleophile, this time carbon N, lone pair on the carbon, negative charge there. Then we're going to show the electrons attacking that carbon. Then one of these bonds in the carbonyl midway is going to come and jump onto the oxygen, dumping the electrons that used to be in that covalent bond onto the oxygen. And we've got our intermediate, where there's a carbon-carbon bond to the cyanide that we've just formed here. The oxygen has a negative charge on and a lone pair. We need to just close that down and make it into an alcohol. So that picks up a hydrogen from a proton, with the arrow originating from that lone pair of electrons and going onto the hydrogen. So now we're going to look at two exam questions to put this into practice. So pause the video and have a go at this first one here. It's a multiple choice question, and remember your aromatic chemistry. Okay, so the answer for this one would be B. And the reason for this is, first of all, let's just draw benzaldehyde. You can see here that CHO means an aldehyde. Then we've got the benzene ring directly attached to it. We know from reactivity that the cyanide will react with a carbonyl, and the cyanide, which is from this sodium cyanide here, form a bond with the delta positive carbon here, as this is your nucleophile and this is your electrophile. So we form that C-C bond here. That was that cyanide, and if we imagine a curly arrow attacking this delta positive carbon. Now you'll notice this carbon has too many bonds around it. We've got 2, 3, 4, 5. So we're going to quickly change that. And then this makes this a H. So we've got a hydroxyl. And the other thing to be aware of is that obviously this is just not showing the hydrogen, and all that's happened is that has moved up. See that that is obviously B. Now the reason it can't be A, C or D is because the carbonyl is intact, and we know whenever we attach a nucleophile by nucleophilic addition to the carbonyl, then it converts into an alcohol. Either form this hydroxyl nitrile, which we can see here as well, or even if it was hydride, and instead of this cyanide you get the hydrogen added on, but you still get this big change of a carbonyl to an alcohol. Obviously be seen in our specific example here, benzaldehyde going to this hydroxynitrile B. Okay, more involved 4 marker, look at nucleophilic addition. I want you to pause the video here and have a go at it. Okay, so the answer for this should be as followed. F is, very well done if you got that right. If not, we're going to go through it right now. We should start by saying there's some really key information in the actual question here. First of all, it's telling you what you should know already. Aldehydes and ketones are reduced by sodium borohydride. That's our source of H-. Key piece of extra information that's beyond the course, but because they've given you it's fair game, is that when used in the presence of a cerium chloride catalyst, this sodium borohydride only reduces ketones. Usually aldehydes and ketones undergo reduction to primary alcohol or secondary alcohol with sodium borohydride, but what we're saying here is this with this cerium chloride catalyst, then aldehydes do not undergo this reduction. We're then told that compound F has this structural formula and that it is reduced by sodium borohydride, so we know it must have a ketone in it. And then we're told that it forms either C, D, or E that we've been given the exact structure for. So it's useful to kind of annotate with the information in text into a more visual form. So all I've done here is convert that into basically this. Now, what this then requires us to do is to work out the reduction of compound F and identify the product that is formed. So before we can even write a mechanism, we need to actually identify what F is. Now, this goes back to our original thing here. Our knowledge that a ketone, when it gets reduced, goes into a secondary alcohol. We know that our product, C, D, or E, must contain a secondary alcohol. We do a quick analysis of C, D, and E and the functional groups that are there. First of all, C has a ketone in, so this would have been reduced if it was the daughter of F, because this ketone would also change into a secondary alcohol. And then the other one is a primary alcohol, so we know it cannot be C. Then if we turn our attention to compound D, we know we've got a secondary alcohol and we have an aldehyde. This is a possibility because going back to our original idea, any ketone that was in F should change into a secondary alcohol. The aldehyde would be unchanged because that does not undergo reduction when you've got this catalyst. And then in compound E, we have both a tertiary alcohol here and a ketone. Now, just like compound C, if we had a ketone in the product, which we do have in E, this would actually be reduced to a secondary alcohol. So we know that that cannot be the product. We know the product can only be compound D out of these three possibilities. So if we draw that as our product in our mechanism and work backwards, knowing that this secondary alcohol here used to be a ketone, that then gives us F, the original reactant. It's this fact here that ketones go to secondary alcohols that has allowed us to draw the actual reactant of choice and also identify the product. So this is a great example of how one little bit of fact of knowing sodium borohydride plus a bit of information given in the question can be applied to a problem-based question. Now, the mechanism asks you to use curly arrows and relevant dipoles. So you'd put a delta plus on the carbon of the carbonyl, delta minus on the oxygen. You would then show the sodium borohydride, the hydride nucleophile, lone pair, negative charge. The curly arrow needs to be clearly going to the carbon, also breaking one of those double bonds in the C double bond O, with the origin of this curly arrow on the double bond going to the oxygen atom. Draw the product of this as an intermediate, show any dipoles in this case, and then all we need to do is close the gap between this intermediate and the actual product D, and that is this oxyanion collecting a proton, a H+, and so we just draw a lone pair here, and we draw that grabbing the H+. And that's all 4 marks there. So that concludes this video on nucleophilic addition of carbonyls, and we've been focusing on the use of hydrogen cyanide to form hydroxynitriles, and then also sodium borohydride to form alcohols. If you found this video useful, make sure that you like it, and then make sure that you subscribe to the channel so you can get new videos as and when they're uploaded.